This is Aryan from EDD Academy, and today we'll be going over related rates part 2. Let's start with this problem. A 1.75 meter tall man is walking away from a 10 meter tall lamppost at a rate of 0.3 meters per second. The man casts a shadow. How fast is the top of the shadow moving on the ground? Now, for problems like these, I always like to draw a diagram, so let's do just that. This is the lamppost that's casting the shadow. This is the ground. This is the man. And if this is the farthest point in a shadow, then I'm going to connect the dots with this line here. So now we have a triangle. But what do we define as variables that we're going to relate in our related rates problem? Well, first of all, I'd like to call the distance between the man and the lamppost x, because here it says that the man is walking away from the lamppost at a rate of 0.3 meters per second, so that would be dx dt. Additionally, we know that it is a 1.75 meter tall man, so that's this distance, and that the lamppost is 10 meters tall, so that goes here. So what about how fast the top of his shadow is moving? Well, this is the top of his shadow, and how fast he's moving is really just the rate of change of this distance that I'm going to call y. And that's because it's just how fast he's moving, or it's how fast the tip of his shadow is moving relative to the stationary object, which is the lamp. So how do we actually turn this into an equation? Well, for these, I always like to use similar triangles, so let's do that. The first one is going to be between the lamppost and the tip of the man's shadow. And the next one will be between the actual man and the tip of his shadow. And over here, we know that this distance is 10, and this distance is 1.75. We know that this is y, and this, on the other hand, is not x, because x is this. It is everything left in y after you take away x, which makes it y minus x. So now what do we want to do? Well, because these are similar triangles, and we know that because they share these two angles, which means they also share this third angle, we can relate their base and height. So we know that base 1 over height 1 equals base 2 over height 2. So we're going to do just that. So y minus x over y equals 0.175 over 10, or sorry, getting ahead of myself, 1.75 over 10, which equals 0.175. And we can multiply out by y and then subtract a y over to get, and then multiply by -1 to get x equals y minus 0.175y. And we can group this out to get x equals 0.825y. All right, and from here we have an equation that we can then take the derivative with respect to time of. And we get dx dt equals 0.825 dy dt. And remember that we have dx dt, it's 0.3, and what we're trying to solve for is dy dt. So we will solve for dy dt. We get the simple expression dy dt equals 0.3 over 0.825, which is 0.364. And in terms of units, we're looking at y over t, which is meters per second. So 0.364 meters per second. And that wraps up this problem. Let's go on to the next one. Water drains from the vertex of a conical funnel at a rate of 2 feet cubed per second. The funnel is 20 feet wide and 30 feet tall. How fast is the water level changing when the height of the water is 3 feet? All right, so for this kind of problem, I always like to draw a diagram. And in this case, that diagram is going to be the cross-section of the cone. So let me draw that. That will be a triangle. Okay. And here we know that the height of the cone is 30 feet, and its width is 20 feet, but we're going to be using the radius, which will be 10 feet. And the water level is going to be this, which I'm going to define as a height denoted by the variable h, and it's going to have a radius r. Okay, so what do we do from here? Well, we have our equation for the volume of a cone, which is v equals pi over 3 r squared h. And what we want to do is be able to change this up so that only one of these variables is here. So we want v equals an equation involving only r or only h. And because they give us the height of the water, we want it to be only h in this case. So that means we are going to relate two triangles once more. So we want to find two similar triangles here. And the way we do that is by looking at angles once more. So that would be this big triangle here and this small triangle. And we know these are similar because they both have a right angle here. They share this angle in common, which means that this third angle must also be in common. Therefore, they have angle-angle-angle symmetry. So what do we do from here? Well, once more, we can relate the base 1 over height 1 equals base 2 over height 2. So we'll take a look at this, and we know that r over h equals 1 over 3, and therefore r equals h over 3. Or sorry, equals 10 over 30, which is 1 over 3, in case you didn't get the middle step there. And now we can plug this into our volume equation here. So we get v equals pi over 3 quantity h over 3 squared h, which is just h squared over 27. And if we combine that with what we already have, we get v equals pi over 81 h cubed. And now we finally have an equation with only two variables that we can take the derivative of with respect to time. So let's do that. d dt of v equals pi over 81 h cubed is just dv dt equals pi over 27 h squared, dh dt, of course. And from here, we know that dv dt is 2 feet per second, but actually it says that the water is draining from the vertex of the cone, so it is negative 2 feet per second because the volume is decreasing at that rate. We also know that the height is 3 feet, so we have everything we need to solve for dh dt. So negative 2 equals pi over 27 times 3 squared dh dt. And now if we simplify this, we get dh dt equals negative 6 over pi, which equals negative 1.91. And in terms of units, it's h over t. H is measured in feet, and t is, of course, in seconds. So feet per second. And that's our final answer, negative 1.91 feet per second. Let's take a look at the next problem. A rocket is ascending vertically while a camera records the launch 3,000 meters from the launch site. When the rocket's altitude is 2,000 meters above ground, its velocity is 500 meters per second. Find how fast the camera angle must change for the rocket to remain in frame. Alright, so let's take a look at how we would draw out this problem. Well, first of all, there's the rocket. And it is at a certain altitude, let's call it A, above the ground. And there's a camera, which is 3,000 meters away. And what we're looking for is the rate of change of this angle theta. So that is d theta dt, and that's what we're solving for. Right, because it's asking for how fast the camera angle must change for the rocket to remain in frame. So how do we relate theta and A? Well, if you remember from your intro trig class, tangent equals opposite over adjacent. So tan theta equals opposite, which is A, over adjacent, which is 3,000. And we can multiply out to get A equals 3000 tan theta. And of course we can take the derivative with respect to time to this now that we have an equation relating to variables. So we get dA dt equals 3000 secant squared theta d theta dt. And from here, what do we do? Well, we know dA dt is 500 meters per second because that's how fast it's rising at this time point. So we can substitute that in, first of all. And that equals 3000 times secant squared theta. Well, first of all, let's start with what secant is. So secant equals hypotenuse over adjacent. And this is the adjacent, the 3000, but what's the hypotenuse, c here? Well, at this point in time, we know that the altitude is 2000, so we can use the Pythagorean theorem to calculate c, the hypotenuse. So we know that c squared equals 2000 squared plus 3000 squared, which means that if you do the math, c equals 1000 square root of 13. So this is our hypotenuse. So we know that secant of theta equals 1000 root 13 over 3000. Therefore, secant squared theta is just this squared, which is roughly 1.44. So we now plug this in, so times 1.44 times d theta dt. And now we're going to solve for d theta dt. So d theta dt is just equal to 500 over 1.44 times 3000, which equals roughly 0.115. And in terms of units, we're looking at theta over t, so that is angle over time, which means it's radians per second. And that covers it for related rates.